Hey, what's up guys? My name is Cherno and welcome back to the Sparky game engine series in which we make a game engine from scratch in C++ and OpenGL. Okay, so last time I asked you guys the question of whether or not you would like an introduction to C++, and well, most of you did. So as you can see from this chart I prepared, and I promise I'll die down with the charts soon. But 98% of you guys wanted an intro video, so this is what this video is. Okay, I'm going to basically try and introduce you to C++ in this video. So first of all, we've got Visual Studio. That's what we'll be using. I've got like a list of things I want to cover in this video. Hopefully I don't go too off topic. I'm going to try and do this within an hour, so we'll see how we go, but hopefully this should give you a pretty good idea of the basics of C++, and it should hopefully let you at least understand the code syntactically. So I'll still explain various data structures and stuff along the way of actually making the engine, because obviously I can't list them all here, that would take forever. But this is more or less going to be stuff like syntax, and I'm going to cover Visual Studio a little bit as well, and we'll get into the differences between Java and C++, because I realize that obviously a lot of you subscribers out there are actually, well, you've been following my Java videos for like 3 years or something, so you're probably used to that, and I'll cover the differences as well. So hopefully we'll get a pretty good thing going, and yeah, so let's see how we go. So first of all, we had this Hello World application from last project rather, or solution from last time. So I'm just going to click on it to open it. By the way, my theme settings there'll be a link in the description to the settings, which will have all this layout everywhere. So that's kind of important. So yeah, but we'll so if you want to match up these IDE settings, basically just download the file in the description, and the previous video actually, which was the setup video, that showed how to import it. So if you want to go back to the previous video and watch that, you'll know how to import the file. All right, anyway, back to this. So let's break this down. Okay, so this is the Hello World application. Obviously I'm not going to dwell too much on a simple application such as this, but nonetheless it needs to be covered. So first of all, we've got an include. This is very similar to Java's import statement, except it's very, very different. So I guess it's not that similar, but we'll cover that in a minute as well. That'll be later on. I've got a good structure for this video going, so it is going to be live, but hopefully it's going to be good. So next we've got this main method. Now, one thing you'll notice, well, you should notice straight away, is that it is not inside a class like it would be in Java. Okay, it is just in global space. All right, there's nothing surrounding this method. Okay, because of that, it's usually called a function. Okay, so a method that is not part of a class is called a function, usually. And that comes more from C, which is, of course, a procedural language. And in that language, you would have things like functions. Okay, anyway, that being said, this is the main method. There are several main methods. There's one, if you want to take in command line arguments, you're more than welcome to. You can actually declare main like this with int argc, which is the count of the command line arguments you have, and of course the next will actually be the actual arguments themselves. So this is a pointer to a, well, basically it's an array of char arrays, so it's an array of strings. We'll cover that in a minute as well, but this is a different main method, which you can also declare, and in this case you can actually take in command line arguments the same way that in Java, of course, when you have the main method you have the string args. Well, this is what this is. All right, it's just that obviously we have no idea how big this array actually is, and we'll get onto arrays as well today, don't worry, but we have no idea how big this is, so we have to have a count here as well. So this is basically args.length in Java terms. All right, that being said though, one thing that is different from Java is that the first string in this array is actually going to be the path to the executable. So if I like, basically once I compile this, and let's just say it compiles to hello.exe, right? The first argument, so args at index 0, will actually be the path to that executable. So whether that, C uses whatever, that like a file path. Which is different because Java of course doesn't do that. So that's one difference to know. So if you actually have command line arguments, they do start at 1, all right? Anyway, that's basically the main method. I'm not going to dwell too much on that, but this is the entry point of our program. When we build and run our application, this is where it starts. Okay, cool. All right, this next line of code is a bit confusing because of the way that it's actually kind of written, because a lot of people coming from Java will probably be scared by these, I don't know, the left angular bracket or less than signs, right? Why are there two of them there? It looks like a bit shift left. I know it's weird. Why are they there? So this is basically just the product of operator overloading, which hopefully we'll have time to cover today as well. So in C++, you can actually change what operators do. And operators, I mean stuff like plus, times, divided by, minus, equals, comparisons. There's way more than that. Yeah, these obviously. And there's just so many operators that you can actually overload and you can change. So you can actually basically use them as methods. So that's what's happening here. Cout is basically having a method which you can call to push hello world into cout, kind of. And it almost looks, if you look at it as like an illustration kind of thing, it's like hello world is being pushed into cout. So pretty fancy, right? It's almost like C++ is asking you to draw it a diagram, but that's the idea. So just pretend you can, literally just for all intents and purposes, you can probably pretend that this is something like that. All right, that's really what it does. It's just that they've overloaded, the standard library has overloaded the bit shift left operator, I'm going to call it, and they've made it take in pretty much anything, whether that be an integer or a string or whatever. All right, that's the idea. Now this is obviously just an end line, so this would be the same as if I kind of did that. This is supposed to be a bit more platform independent and system independent, so you recommend it to use that. Also, it probably makes a bit more sense because it says end line and not \n. But that's the idea. Okay, system pause, we covered that. That basically just pauses our console. It's Windows only. Now the other thing that we should mention is that we return an integer. All right. Which is interesting because, well, I just minimized Visual Studio. Sorry about that. Because in Java's main method, it's a void, right? Which means it doesn't return anything. But this does return something. It returns 0. So this is, the best way to compare it to Java would probably be saying when you type in system.exit, you give it a code, whether that be 0 or 1. Well, this is basically the same thing, right? So 0 is supposed to mean it's a proper exit, as in everything went well, the program exited correctly. But something like 1 or -1 or really anything you want is supposed to mean that something went wrong. So if we do something like, if, I don't know, if you have something that evaluates to false and you decide to return 1, for example, obviously that will terminate your application, okay? Because there's nothing, it won't do anything else that's in the main function here. And then, yeah, so basically the integer you return is supposed to act as like an error code. So 0 means everything's okay. Cool. So that's basically the little hello world application explained a bit more in detail. So let's move on to a few different things such as data types. So we have a lot of data types. I'm not going to cover this too in depth because, again, if you're used to literally any other language, this will be easy. Obviously, we have stuff like integers where we can set them equal to something like that. One thing I want to mention is we actually have another type of integer in, another type of integer data type, let's just say, in C++ and in C, where you can actually set something to be unsigned. Okay. Now, if something is signed, okay, it means that it basically can be negative. Unsigned basically says this number cannot be negative. Now, an integer usually is 4 bytes, okay? So it ranges from a value of about like 0 to roughly 2 billion-ish, right? It ranges from -2 billion all the way to positive 2 billion, roughly, right? Now, and the reason it does that is because that's the maximum that we can store in 4 bytes of data. That being said, if we were to mark it as unsigned, right, that means it can't be negative. So all this extra data that we could possibly store basically gets, since it can't be negative, basically gets pushed over here. So suddenly we can store numbers twice as large, right, with the consequence of not being able to store negative numbers. Okay, so that's, for example, an advantage of using unsigned types. You basically can store more data, right? But you also prevent people from accidentally setting stuff to negative, which is also really important, okay? So that's one thing I want to mention. And this works with stuff like longs as well. Now, longs are usually 64 bits, right? 8 bytes. But Visual Studio doesn't like to make them 8 bytes. Visual Studio likes to make them 4 bytes, or the Visual Compiler, I should say. Visual C++ compiler. it likes to make them 4 bytes, okay? So if you actually want something that's you want a 64-bit integer, you need to mark it as long, okay? Don't ask me why they made that decision, they just did. That's the idea, all right? In a 64-bit application, it might be a bit different. I'm talking about 32-bit applications right now, so... but that is the idea, all right? So that's something to pay attention to as well. So if you're used to the long in Java and you want to store something similar, you might want to store long. But then again, there are a million different other data types in C++, such as big integer, for example. And again, that isn't really part of C++ per se. It's probably part of the Win32 API, I'd say, maybe that one. I'm not sure, but big integer, for example, is something capable of storing more than 4 bytes of data. Anyway, that being said, that's that. We have floats, okay? So floats are exactly the same. If we have a float, we can set it to something like that, right? It should have the F to reinforce itself being a float, right? A double is the same, right? So the key difference here is this is 32 bits or 4 bytes. I'm not even gonna write that. And then this is 64 bits or 8 bytes. Okay, now when you're checking out data types and you want information about them, one thing that you can actually do is use the size of operator. So not really an operator, but it's more of a keyword thing. But basically, you can check the size of pretty much any variable or data type in C++, all right? And that'll give you back the size in bytes. So if I was to, for example, check out the size of an integer, as I just mentioned, which is 4 bytes, and I just hit F5 to run that, one thing I'll do quickly though is I'll make that font a bit bigger. So, why is there no... Do I have to do this? That's really annoying. There should be... There's usually a... This is the Windows 8 console though, so it's probably a bit different. But usually there's a font size thing, which is annoying. Oh, here we go. No, that's because it was raster fonts. So we'll go Consoles and we'll make it like 28. All right, so hopefully that's big enough. But 4, right? So it gives us the size of the data type. So if I type in something like long, for example, right, we'll get, again, 4, because that's what the visual compiler will do. If we type in long, we should get 8. Okay, there's our 8. You can also check other stuff. So, well, you know, if we have, let's go down the spectrum a bit. So after int, we've basically got a short, which is 2 bytes, and then we've got a char, which is capable of storing integers, of course, and that is a 1. Okay, that's 1 byte or 8 bits of data. All right, cool. Anyway, so the size of is a very important thing for you to use, because we'll see it's got some use with arrays, but usually it's really good for creating buffers and stuff and sending that stuff to OpenGL, because anytime you want the size of something in bytes, the size of is just really important. Okay, again, we do know the size of a char is 1 byte, so we can just, for example, use the 1 there or something, or define like a constant that stores that, but the size of just guarantees that it's actually going to be correct. So anyway, that being said, next up we're going to probably talk a bit about probably I'd say the preprocessor. So one of the biggest differences between C++ and Java is C++ has a preprocessor, okay, as does C and stuff, but we're talking about C++. So anything you see with a hash is called a preprocessor term, or preprocessor command. So that's anything starting with a hash. So anything that starts with a hash, you can notice, does not have a semicolon at the end. It isn't really a normal line of code, because what happens is this does not actually occur when you're running the application, okay? This is something that happens, it's called the preprocessor because it happens at compile time. So it happens before compile time, really. So it happens before our code is even compiled, okay? So when we tell Visual Studio to build our application, what it does is it basically scans for these hashes, okay? And when it runs into a hash, it evaluates whatever the hash tells it to do, and then it'll probably loop through the code again to make sure there aren't any other hashes, and when it's content with that, it will actually compile the code, all right? That is how it works. So this stuff does not affect runtime at all. It doesn't affect compile time at all. This stuff gets evaluated before our stuff even gets compiled, which is why when you use these, as we'll see in a minute, it's essentially really powerful because you can tell it how to compile in a way. So we'll talk about that as it comes up. But the first thing is we're actually including a header file. So what does hash include do? And the best way to demonstrate this is probably just to add a new item. I want to add a header file. We'll talk more about header files in the future, but I'm just going to call this header.h. All right. And in this header file, all I'm going to do is I'm going to basically type something like, I'm going to make a function, right? So let's just say void a, and then all I'm going to get that function to do is print out something like hello world, right? That's all I'm going to type in there. And then I'm just going to close the header. What I'm going to do now is I want to include that file. So header.h. So if I include header.h, and then over here, I call, so this is kind of like Java, right? Pretend we declared a method called a, I should probably just call it print or something, in our header file. Pretend we just did it in another class or something and we're calling it now. So if I go print right now and I run this, it's going to print hello world. Now, one of the things I want to mention is what actually happened there. What did it do? Okay. What it did and what include does is it simply scans the file. So it looks at header.h, which is this file. It control A, then it copies it. It selects everything in the file, copies it, and pastes it in. That's all it does, which means our application is essentially looking like that, and it will do the same thing with IOStream, okay? It simply pastes it in, okay? If we run this now, yeah, we get the same result, right? Because that's all it did, okay? That's what it does. A more extreme example might be something like, let's just say we've got a bracket here. That's it, we've just got a bracket. And I'm, for some reason, wanting to do this. Again, there'd be no real use to do this, but let's just say I will print our normal hello world. Oh, I'll just print hello. Right, and then all we've got here is a curly bracket, and then instead of this curly bracket, I'm just going to go ahead and include header. All right, will this run? Absolutely, okay? Because all it's doing is it's taking in, it's copying whatever's in this file and it's pasting it here. And look at that, that's our application, okay? So again, this looks ridiculous, but yeah, that's what it does, all right? And it's totally possible to do pretty cool stuff like that. So Java can't really do anything like that. So hash include is one preprocessor statement. The other, well, there's tons, but another really useful one is define that you probably might have seen. So define does a similar thing to this. So it does a similar thing to include, except it doesn't read from a file, it reads from what you give it. So if I say something like define width 800 or something, and then I print out the width over here, and I run this, obviously it's going to give me 800. Now, how is this different from me declaring like a constant or something? Well, what this does is it looks for width. So it doesn't find it in place, basically. It looks for width and it replaces it with 800. Okay? So what happens is when this gets compiled, it will look for width, it'll replace it with 800, and there we go, it's done. Okay? That is what happens. So we might as well have written 800 there because that's how the code gets compiled. Okay? Similarly, it's kind of ridiculous. So if I declare Cherno to be int main, I can just write Cherno here and then compile it and it'll run. Okay? Let me change this back to hello. Yeah, I can also even include that bracket and make it look even more ridiculous. And run that, and that'll work. So it's pretty ridiculous what you can do with this stuff. Again, in this case, it's ridiculous. It's probably incredibly useful for stuff like obfuscation as well. You can make code really unreadable with it, but that's not really why it's used, okay? It's used for scenarios in which we essentially want to either define method. Well, I'm not going to get into uses just yet. You'll see me use it a lot during the later videos of the Sparky engine, but it is incredibly useful for things like this because it's basically, again, it can be used as a constant, but remember it happens before code gets compiled. All right, cool. So that's define, right? I guess I should probably, I'll mention one useful use case. So let me bring back our main method, or our main function rather. One cool use method is, let's just say we had, or use case, let's just say we had like a logging thing, and all this will do is it'll print out something like, it'll print out our X. All right, if I go ahead and log I can log something like, but yeah, you can take in parameters. You can take in as many parameters as you want. You can even take up variable amounts of parameters or arguments. But if I log something like hello now, you can see that it becomes, well, it works the same way, but it's like this. So why wouldn't I just make a function that does that? Well, obviously a function would require a function call, okay, unless it's inline. And in fact, the compiler will probably optimize that anyway, but we're not going to get too advanced here. The idea is that this is essentially better than a function call because it isn't a function call. So the computer doesn't actually have to call a different function. Remember, when it evaluates this, it just copies and pastes this, and of course the x becomes hello, and that's it. So it's the same as if we did this, whereas if we had a function call, it would actually have to go ahead and call that function. So that's an important thing to note as well. Now, the other preprocessor statement that we're also going to integrate with this log system of ours that we just created is basically if. Okay, there's one called if def, there's if ndef, which is if not defined. That's if defined, but we're just gonna look at if right now. So if something is true, so we can put a condition here. Remember, it can't be like a variable in our code because this stuff happens before the code gets compiled. So it has to be another kind of thing. And also these are usually called macros, by the way. So this log would be a macro. But anyway, if something is true, so I can just write if 1 because 1's going to be true, right? Then I can choose to do certain things. So for example, you can see this log, right? If 1, I'm going to log it. And then you have to put an ndif at the end. So if true, I'm going to log that, which means that if that is true, this code will be included in the compilation. If I were to shut that off, you can see the code kind of goes, like the saturation kind of dies down and it becomes a bit darker. That's just Visual Studio telling us that it's not going to, it's off, essentially. It's been turned off. If I run this now, you can see there's no hello. So what happens is, if it encounters an if0, again, it just removes that code. So this code, what's important to note is this code isn't just not running, it does not get compiled. It does not get put into our binaries at all, okay? That is just simply not present. It's very different than if I do an if statement, okay? If the compiler encounters something like if false, it will probably just remove that whole block, okay? But it is very different because it happens before compilation, okay? It's as simple as that. All right, now, how is this useful? Well, let's go back to our logging system. We only want to log stuff, like errors, for example, if we're actually in a debug build, right? If we're releasing this or we're distributing it, we don't want to have all these logging things everywhere, right? We want to basically have a way to switch that off. So what we can do is we can define a, like a flag, such as debug1, so that means where debug mode is on, right? And then we can say over here, if debug, then we want to log, all right? In fact, I'll show you guys a different way to do it first. So if debug, then we log something like hello, otherwise we don't. So if I run this, you can see we say hello. If I switch debug off at the top, there is no hello, okay? Great. Now, a better way to do this would be like this. If I put this around the actual definition, because otherwise we'd have to do it every place log is used. And I do something like this, where if debug, we'd define log. And then what I can do is I can actually use an else, right? We'll define log as well, but we'll define it to be empty. So you can see it doesn't actually have anything. So when it finds and replaces it, it'll replace it with nothing, essentially. That's our plan. So we'll replace it with that. If debug is turned on, yep, hello works. If I turn it off, whoops, then you can see there's no hello. All right. So this is a nice way of basically having like a logging system where you can actually disable bits of your code really easily. Okay. So that's an actual real world usage of macros and other preprocessor statements. Okay. So that's essentially the preprocessor. You can play around with this like, you know, however you want. We'll be using it extensively during the engine development, of course, for stuff like logging. But that's a general idea. So remember, if debug is off, our code that actually gets compiled looks like this. Yeah. If debug is on, our code that gets compiled looks like this, with the X being the hello. Okay. And that's it. So just remember that. All right, cool. So that is the preprocessor. Pretty cool. And I wish Java had something like that because it would make it just so much better. All right, anyway, that being said, let's move on to a few other things such as functions. So I mentioned functions. I mean, we did one in the header over here, but functions are like methods in Java. So they're basically bits of code that we can call and it will run like a nice group of code. It lets us basically write a bunch of code in a statement, of course, and then whenever we call that statement, it will execute that code. Okay, for those of you who just don't know what they are. So one thing that might be different is you might be noticing that I'm not writing stuff like private void or whatever. The reason is there is no such thing as that because we're in global space right now. We're not in a class. Something can only be private and public and protected or whatever if it's in a class. Okay. What are we at? 25 minutes. Okay. I'm gonna try and speed this up a bit. So yeah, you might want to watch this video like multiple times as well because I'm going to start doing this a bit faster. But anyway, public, private, protected, whatever, that can only exist in a class. Okay, we're not in a class. We're in global space right now. In fact, this will probably tell you we're in a global scope. All right. But when I declare a function here, such as a, right? Again, it doesn't have any modifiers because we're in a global scope. But the idea is if I put something like if I put our log into here, yeah, then all I have to do really is I can call that function, and as you can see, it will print hello. So functions work the same way that they do. Note, if I put it over here and run it, it's not going to work. It's going to give us a build error because it doesn't find it, because it compiles from top to bottom, basically. So this is where a function prototype comes in. What you can do is if you really want to have something at the end of this, and it's kind of important if you have two functions that interact with each other, because then you can't really put them in one order. So just a quick example, if I had B and I wanted A to call B and B to call A, so if I had that calling B, then you can see that there's no way I can actually call A, because A wouldn't be defined until B is defined, but I also can't define that first because I want B to be defined. Anyway, we get a big mess everywhere. So there are these things called function prototypes. So if I really wanted this to be here, what I can do is I can actually define a prototype for the function A. So a prototype basically tells me all the information I need to call the function without actually having its implementation details. So if I type in something like A, it's kind of like an abstract method in a way. So I don't give it a body. I do that essentially, void A, okay, and that's it. And if I run this, you can see it will work, okay? If I didn't have that, again, yeah, build errors, all right? Cool, so that's an important thing as well. Functions can have return types, obviously, so I can return an integer. So if we have a simple addition function, I take in two integers and I add them together. 1 and 2, for example, and I print that out using my log function, or my log macro. We get 3. Yep, cool. That we can all agree that 1 plus 2 is 3, hopefully. If not, then I can't help you. Please read a math textbook or something. But yeah, so that's an example of something that returns something like an integer. All right, cool. Anyway, those are basically functions. Let's move on to some more exciting things like pointers and memory addressing. So I'm gonna have to just take a drink real quick, but get excited. So one of the biggest differences as well between Java and C++ are we have things like pointers in C++. Now we actually do have them in Java. It's just that we don't get control over whether or not something is a pointer or not. Java automatically sets things to be pointers and some things not to be, okay? Which is a bit annoying because I'd like to have that control, but apparently Oracle or Sun Microsystems back in the day does not think it's good. I don't know. Anyway, the point is, pointers. What are pointers? Pointers are simply memory addresses. That is it. A pointer is a memory address. Okay. Also, as the name might imply, it's usually a memory address that points to actual data. So, to give you a basic example, if I have an integer called a and it's set to something like 5, all right. If I were to print out the number, or if I were to print out this integer, we would get 5, right? Now, a pointer to this integer would be declared as follows: int asterisk, all right, p for pointer equals the memory address, so ampersand a, all right? And if I print that out, we'll get this weird hexadecimal number. So this hexadecimal number is actually the memory address of A, okay? That's all it is. A lot of people get incredibly confused with pointers. Please don't. A pointer is a memory address. That's all it is. Now, if I want to access the data at that address, then I have to do something called dereferencing, okay? The way I can dereference a pointer is simply by sticking an asterisk out the front of it, okay? So if I run that, you can see I'll get 5. 5 is the value of A, all right? So I'm going to draw you guys some diagrams here. So essentially, what we've got is we had an integer. That is just too small. We had an integer, and it's like, here we go. I've never drawn on this account before, so it's all weird. But essentially, yeah, so we had an integer called A, okay, and we set it equal to 5, right? Then we had a pointer, which I'm just going to denote like this, which we set equal to the memory address of A. Now, in our actual memory, right, if this was our RAM, this is just a block of RAM, okay, what we have is we have certain addresses. So, I don't know, FF like A0 or something, we'll say it's one address. Then we'd have something like FFA1 or whatever, which would be the next byte, right? So these are addressed as bytes, first of all. That's the minimum form of addressing we can do. We can't address bits of memory, only bytes, okay? That's the shortest, like that's the most precise addressing we can do. So what we have is something like an integer, which takes up 4 bytes. So it takes up this much memory, okay? All of this is that integer. It's stored over here, okay? And just pretend that 5 takes up this and this and this as well. But we've got this 5 here, right? So the actual A is essentially this, right? Whereas the pointer, or the ampersand A, is actually this address. So what happens is, if we want to, it's almost like arrays, yeah? So if we have an array of data that is something like, let's just say it's an array of 3s, yeah? One thing you might have realized, right, is we have an index for that data. Yeah, 0, 1, 2, 3. And I apologize if my face cam is in the way. But we've got indices for, you know, in our array. And this would be an array of length 4, for example, right? Same thing applies here. This pointer is like the index of our memory, okay? It's just an address. No need to freak out about it. It's just an address. It's like just like one of these. It's in hexadecimal format though, and obviously in this scenario, our RAM is just one huge array of data, okay? That's how it works. So when we dereference a pointer, so if this was declared an int pointer here, if we dereference it and we print it out, which is what we did, so let's just say int b will equal the dereferenced p. What it does is it goes into that memory address and it takes in the data. So it's like looking at the actual value at an index in an array, right? It takes that data and it gives it to us, okay? And that is what dereferencing does. Now, there are a few key things to note here. If I dereference p and I set it equal to something like 6, right? What is it going to do? It's going to look at the data at index FFAO, or memory address FFA0, right? And it's going to change it to 6, yeah? Int A has the exact same memory address, because remember, this pointer is simply the memory address of A, right? So if I change that, the value of A is actually going to change to 6, all right? That's another really important thing to know, because it is the same address, yeah? If I take the memory address of A and put it into a pointer, which is just capable of storing a memory address of an integer, right? Because it's an int pointer, then it is the same, it points to the same piece of data, okay? That's really important to know. Now, if I do something like int b, and you can see I'm dereferencing it, when I run int b, it's going to allocate a new block of memory, right? And then it's going to grab the data and assign it to that new block of memory. So if I go int b now and I change b or whatever, that's a different block of memory already, because essentially it's been copied, okay? So that's something really important to know as well. We'll go back to the diagrams probably in a minute, but please remember that, okay? Because a lot of people are strangely confused about this stuff. So why is this stuff useful? Why would I want, essentially, I've created for myself basically an alias, all right? Why? Why is that useful? Well, we're about to figure out why that's useful. So if we have something like it's okay. So let's just look at one use case, right? Functions. What if we want to take stuff in as parameters, right? Let's just say I have a function called increment, right? And it will basically increment a value, yeah? So we'll go ahead and increment the value, yeah? So I have a value, it's 5. I want to go ahead and increment it. So I want to increment A, and then I want to print A. Will it be incremented? No. Okay? Why? Because when it's passed into this function, increment, it gets passed by value, right? The address simply gets copied. And when we reach the end of this scope, which is at the end of the curly bracket, this value variable, which we copied our data from A into, gets destroyed. Okay? So this plus plus literally does nothing. Okay? It increments value, and value will be 6 here, but then value gets just wrecked here. So it's gone, right? There's absolutely no use in, it does nothing, right? So what we want to do is instead of giving it, instead of making it create a new variable and then incrementing that, we want it to increment our A variable. So how do we do that? Well, we can give it the memory address of A and then tell it to increment the data at that memory address. So how do we do that? Well, we use our little pointer thing. By the way, a lot of people put pointers, some people put pointers in the middle like that, some people put them here, some people put them here, okay? It's up to you how you put it. The more correct way to do it is actually putting it like this, because if you have multiple blocks of pointers, unfortunately the way it's hooked up is every single one of these need to get an asterisk next to them. So if you do something like that, only A will be an actual pointer. Okay, B will not be a pointer. So that's why the recommended method of doing it is like this. I do it however I feel like doing it. So in this case, I did it like that. Just don't get too upset, okay? It's just a convention. Okay, so if I do this, and then I pass in A, of course, A can't be passed in anymore because A is not a pointer to A. So obviously a pointer is a memory address. So it wants the memory address of A. If you put an ampersand next to an existing variable like this, it will get the memory address. Okay, you can actually use ampersands to declare references as well, which we'll get onto. But that's the idea, okay? So if we do something like this, it will take the memory address of A, which is exactly what a pointer is. So of course the data types work out. Now if I do something like this, we'll still get 5, right? Because what I'm actually doing is I'm actually incrementing this pointer. So I'm incrementing a memory address. I'm changing it from 0, I'm changing it from like FFAO to FFA1, all right? That's all I'm doing. So let's not do that. Let's dereference it, okay? Is this correct? Well, not really, because what it will do is it will do the value plus plus first, so it'll increment the memory address and then dereference that new memory address. We want it to dereference first and then add. So if I run this now, we should get 6, okay? And if I run increment again, or a few times, we should get 8. All right, there we go. This is what I call a messy way of doing things, because as you can see, we need to use ampersands, we need to dereference things. It's not really very elegant. So what we can do instead is use a reference rather than a pointer. So a reference is much like a pointer, except it has an ampersand, okay? An ampersand, in this case, makes the integer a reference to an integer, okay? It is not the same as this ampersand, which takes a memory address of a variable, okay? It's very different, all right? It's called a reference. So basically what this means is I no longer need to have these ampersands here, and I no longer need to dereference things. So basically what I'm saying is, for all intents and purposes, this is a normal integer, yeah? But when I do something like this and run it, you can see we remain at 5. When I stick this ampersand here, we go all the way up to 8. Pretty cool, huh? So yeah, just by sticking an ampersand there, I'm suddenly passing this by reference, which means I'm not making a copy of it anymore. I'm not making my own variable called value within this scope. I'm actually passing in a reference to an existing variable. Cool. So does that mean that we should always do stuff like that? When should we pass things by reference? When shouldn't we pass things by reference, right? The basic rule of thumb is that you want to pass things by reference when you need to modify them and you want the actual variable you pass in to get modified. So for example, this use case, that's an acceptable use case. You also want to, you also want to pass them in by reference when you're not going to modify it, when you're simply going to read it, because there's no point in making a copy of it. It has to copy it in memory, which takes a bit of time, and it has to store it in memory, which takes memory. If we're not even going to modify it, if we're just doing something like a plus b, do we really need to copy these variables? No, not really. So we use references, for example, right? I'll talk a bit about that in a minute, actually, because that has a bit of a trick. But when do we want to pass things by value then? Essentially, when we want to modify the variable, right? But we don't want to apply the changes to the other scope. So when we want to modify a variable such as value, but we want it basically to, we don't want to change a though. Yeah, we want to only change our internal kind of value variable, all right? So that is a few examples for you guys. Now, with our adding of things, if I want to, let's just say I want to add, we've got 5 here, I want to add like 3 to 5. So I'll have another thing called int b equal to 3 or something. And then I want to add, that'll return the result. So I'll log add ab, all right? It gets passed by reference now, as you can see, and we get a fantastic result of 8. The problem with this is that, and it's technically more efficient than what we had before if we remove this, right? Because if we remove this, it means that it actually copies the data, right? We don't want it to, so we use an ampersand now. It's more efficient. It doesn't have to copy the data, and it doesn't have to store additional a and b variables in memory. So it's more efficient now. But we do lose a bit of usability here because we actually can't pass in something like 3 now. The reason is it wants an actual reference to a variable. All right. Usually this is not a big pain because we could just declare something like this here, as we have over here, and pass in b instead, right? And that's totally okay. But yeah, sometimes you might want that there. Okay, in that case, you actually have to do this because it's no longer making a copy of an existing variable. It's actually assigning 3 to this b, kind of in this fashion. All right. Anyway, that is basically referencing and a few other things. So let's talk a bit about const and the whole constant thing, because that is quite a long thing to talk about. So okay, so we've got in value, that's incrementing. That's a cool function we've got there. Let's take a look at add a bit more. Now, our integers here in a and b, let's just say we do want them as reference because we're super cool. And I'm adding these b, I'm adding a plus b, and it's giving me 8, which is fantastic. So what if, so const, let's talk about const first of all. So const int c for const equals 2. Const is kind of the same thing. It's actually quite different, but for now, it's kind of the same thing as final in Java, okay? Which means that once you set it, you can't really modify it. So if I try and change c to 2 or something, it's already 2, but if I try and change it to like 3 or something, and it's marked as const, you can see it has to be a modifiable local value, right? Has to be modifiable. It's not. So that's an error. You know, I can't do anything with it. I can't increment it. I can't do a lot of stuff with it. Okay, it's basically marked as final, and I can't change it. Cool. So over here, yeah, in parameters, I can actually declare them as const as well. I mean, you can in Java as well. You can declare parameters as final, but anyway, const int reference a. Okay, so this is now building up the amount of modifiers it actually has. This right here, what you're looking at, would be the actual correct definition of an add function, because by putting const here, I'm basically promising to whoever calls a function, I will not modify your value. So you're safe to give it to me by reference. Again, if it's like this, that makes no sense. Having a const int a doesn't really make any sense, all right? Whereas if I have something like this, yeah, a const reference, because the reason I say this is because this will actually scream at you for not having a const, and you probably have to mark this as const. But anyway, the point is, if I've got a reference, obviously that leaves the user of this, or the caller of this function, quite vulnerable because there is no promise. I'm basically letting you read and write to my a variable, which is over here, but I might not want you to change it. So what, should I make a copy just to be safe or something? Like it's, yeah. If I put a const here though, I'm saying I'm taking in your variable by reference because I don't want to make a copy of it, but I'm not going to change it. I'm not going to modify it. Your secret's safe with me. Okay, I'm not going to change it. Because I can't. Again, I can't. Now, I say I can't, but this is C++, right? You can do anything, can't you? Unfortunately, yes. So there is actually a way to modify A, even though this is the case. So if I do something like this and we just test this out, it gives us 8. What I could do if I was really, really, really naughty is I could use something called const cast. Okay, so if I have a reference to a variable and I'm going to say just best, because this is definitely what you should do at all times in C++. And I decide to const cast this, so the data type I'm casting to now is an int reference, and of course I'm casting A, and then I increment best. Yeah, and then I return best plus B, or in fact, I don't even have to do that. All right, I apologize for that. I just had to go handle something, but we're back. So if I do this and I const cast int reference to this, and I increment best, right? And if I go ahead and let's just take this out for a minute. So we'll still call that out function, of course, and then we'll just check out A. You can see that A is 6. All right, so we've actually, you know, it's const int, right? You can't change it. Wrong, you can. Don't do this ever, pretty much, okay? You can use const cast to add constness to something that isn't const, right? But you can do that implicitly anyway by just simply saying const, you know, const int A equals something that's not const, right? But don't do this because you shouldn't, basically. It's one of those things you shouldn't do unless you've got a very good reason to, which is usually not. Usually there are no good reasons to, but that's the idea. Okay, so there's always C++. There's usually an exception to the rule. Okay, cool. Anyway, that's what const is. Now, what we can actually do, and this will become more apparent in a minute, is we can actually mark things as const like multiple times. So if I do this, that's totally valid. So I can mark something as const int, right? This is probably a better example with some pointers. So int p or int pointers will take in, let's just say, a const int pointer a. All right. So if I have, if I want to take in a pointer and it's going to be const, and I do something like pointers a, memory address of a rather, right? If it's const, it won't let me change a. So if I try and dereference a and change it to something like 2, you can see that gives me an error. Okay, so I can't change the value of a if the const is at the front like this. Whereas if we don't have a const here, whoops, but we do have a const here, you can see it lets me, right? But I now can't change the actual value of a. As in, it doesn't let me do that. In fact, that's really mean. So let's just say something like this, 3. Yeah, it doesn't actually let me do something like this. It won't let me take the memory address of something. It won't let me reassign the actual pointer. Yeah, so the actual pointer it won't let me change, but it will let me change the value at that pointer, as you can see. Yeah, now if I had const both ways, like this, I can't do either of these things. Okay, which is another important note. Okay, so that is what multiple constants does. You can actually also have a const over here. That's if this was in a class, right? Which would mean that this function can't actually modify any members of that class. But we'll get onto that in a minute when we look at classes. Okay, so that's what const does, and that's why you can have it multiple times. So one of them affects, or one at the front affects the value at that pointer, whereas this actually affects the actual pointer itself, right? The address itself. All right, cool. So that's constness. One thing I want to mention with references is you can't actually reassign a reference. When I declare something like a, and then I'll declare a reference to a, like r, right? Which is just going to be that. If I were to, let's just test this out. Okay, 5, right? If I were to change r to 2, yeah? You can see a, I'm still printing a is now 2, right? Furthermore, if I suddenly want to, if I have b and I'm like, oh, you know what, there's r, I want it now to be the reference of b, right? Wrong. It will simply change a to 10. Once you assign a reference like this, you cannot change it. It will always be the reference of a. That's one of the reasons, if you don't want to do that, you can definitely settle with a pointer. all right? Because obviously I can reassign the pointer. If I was doing something like this, it would look like that. And in this case, it would change A to 10. But again, if I wanted to take the reference of B, I simply do something like that. And voila, A is still 5, all right? So that's an important note as well. Cool. So that is hopefully all you need to know about pointers, referencing variables, and constness. So let's move on to classes and other kind of structures of data. So classes are declared as follows. So we'll keep these for now. If I make a class, I declare it by typing in class. I then give it the name of the class. So we'll probably just call this entity. And I can declare. One thing I want to mention is that you can see there are actually semicolons at the end of this. That's very important. Java doesn't have these, C++ does. So we have this here. If we want to declare something as a private member, we type in private followed by a colon, right? And then we say XY, for example, will be private members. And then if I want to do public, I just declare public. And then I, for example, want to make the constructor public. And anything I put under here will be public, right? I can use these keywords multiple times, so I can use private twice. It's not like I have to use it twice. And you'll probably see me use it twice for organizational purposes. So for example, I might want public static fields or members up here. Then I might want private members. Then I want public methods. Then I might want like public private methods. Then I might want like public static methods. Anyway, the point is you can declare these multiple times, okay? And the other one we have is protected. So if we have an entity and it has a protected int x and y, and we've got this thing here, right? Let's just take in something like int x, int y, or we could be even better and take in a const. I'm not gonna bother with that now because I do actually want them to be done like this. If I go this, I can't actually go, okay, so let's talk about this a bit as well, but I have to go this arrow x equals x, and this arrow is going to be well over an hour, unfortunately. But anyway, this arrow y equals y, which will set these fields, and then I might have something like int get x, which will return x. In fact, I'm just going to write this like this to not take up too much space. And we've got a getter for y as well, which will return y. All right, cool. So we've got a pretty cool class now. These arrow operators, I'll explain them in just one second, but let's just say how do I declare this entity, right? We've got this class now called entity. This is the declaration for the class, right? How do I use it? How do I make a new instance of this class? Well, glad you asked, because it's really simple. We just type in entity, and then E. Now, that's like the name of it. Now, that is, if we had a default constructor, let's just say we do have a default constructor. So we have a default constructor which sets x to 0 and y to 0. That's valid. And if I go something like e.getX, yeah, in Java, this would probably give you a null pointer exception. In C++, it totally works. 0. Fantastic. Why? What's happening? Well, we don't need the new keyword. Okay, the new keyword does something a bit different, which I'll cover in a minute. But when we make an object, we can make it like this. Okay, this is called making it on the stack. So this is called a stack object, okay? That's just the memory space that it's made in, okay? So when we do something like this, again, we don't need equals. But now what if we don't have a default constructor? What if we actually do want to specify parameters? Well, it's pretty simple. You just put in brackets like this and you specify it to be at 5, 8, for example. That's it. And if I print this, we'll get 5 for x, okay? Cool, pretty cool. Yeah, this might look a bit weird because in Java, you'd be used to declaring it like this, okay? In C++, usually we declare objects like this, okay, if they're not pointers, and we'll move on to that in a minute. So this is one way we can declare this entity variable and print it. There is another way, okay? So this will be on the stack. We can also declare an object to be on the heap, okay? Now the heap is a big form of memory that we actually control ourselves, okay? In C++, or in any language, this data, entity E, right, it obviously allocates a bunch of memory to store 2 integers and possibly some class overhead, right? But for our example, 2 integers is what it stores in memory. It allocates some memory to store those 2 integers, and that memory will be active and it will be reserved for just this entity called E until we reach this end of scope, right? This end curly bracket. When we reach that, anything that's here that only exists in this scope, that was declared in this scope, or any parameters that aren't references, will be destroyed. They'll be destroyed. The memory will be deleted, okay? They won't exist anymore, okay? So what happens is in Java and in a normal stack-based object is when we reach the end of this, our object dies. That's it, it's gone. The memory is removed. Now, if we declare an object on the heap, it works a bit differently because we actually have to manage this memory manually, okay? So if I make an entity, if I make an entity, let's say player, right? And I want to make it on the heap, I have to mark it as a pointer, all right? Like this, or like that, right? Up to you. I have to mark it as a pointer and I have to set it equal to a new entity. So this is more or less kind of Java's syntax. Let's just put this player somewhere else. So 8,8 maybe. That will be made on the heap. So what happens is this object actually won't get deleted until I call delete. So when I say delete player, that's when it will get deleted. So you have to remember to do this, okay? Most operating systems, like Windows, will probably clean it up for you anyway, so it's not really a big deal to delete objects. But if it's a running application, you want to delete it, because if I call something like this every frame, for example, in a game, and it specifies an entity but doesn't delete it, that is essentially a memory leak, because it's allocating more and more memory. It's not deleting the memory when it's done, though, okay? So, prime example, we have something like print player. Yeah, if we have a function such as print player, and it does something like this, and then let's just say it logs player.getX, and that's all it does, right? We have to use the arrow operator here. We'll get onto that in a minute, I promise. But if we do something like this, and we run print player every frame for some reason in our game, yeah, this won't get deleted. It'll still take up memory. So every frame we're adding, like, I don't know, let's just say 8 bytes of memory. Every frame, so 60 times a second. Okay, that becomes a lot more than 8 bytes. That becomes 480 bytes of memory every second. Half a kilobyte every second. That is an example of a memory leak. Okay, we don't want to do that. Once we're done with it, we've done all we have, we've done all we want to delete it. Otherwise, it won't get deleted, okay? In this case, you would never declare an object as a pointer. You would declare it like this, because if you declare it like this, okay, you don't need to delete it. It does it for you. So most of the time, you want to let it handle stuff for you, okay? So that's an important thing to know, okay? Cool. So let's quickly talk about the arrow operator. When I declare something as a pointer like this, I have two ways of actually accessing it. Remember, this is a memory address. It's a memory address, right? So what I want to do is, if I want to access it, of course, I have to dereference it. So if I want to increment the player's x, I dereference player. I can't actually increment its x, but if I want to get x or something, I do something like that. Okay, and then it'll retrieve the x of the player. Now this is a bit annoying, this syntax. So what we can do instead is we can use the arrow operator, okay? And then that does the exact same thing as a dot, but for pointers, okay? What it actually does is it'll actually look up, it's a memory address, so it'll look up the correct offset in the memory address and find the variable, or in this case, function that we're looking for, okay? That's how it works. But the idea is it's an arrow operator, and you use it when you have pointers, such as for classes, okay? Awesome. So that's that. So yeah, just remember, if you use anywhere you use the keyword new, basically, you want to use the keyword delete. So new and delete should go hand in hand, okay? If you're not doing that, you're doing something wrong. Cool. All right. So, to make this a bit more correct though, what we really should have done is, this get function doesn't actually modify int x and y, does it? It doesn't, no. It doesn't, right? It just returns values. It doesn't modify x and y. So what we should have done is marked it as const after, you can see after the definition, we've marked it as const. All right? What that does is it says this function will not modify this. Now, why is that important? You can see it still works. Good. Why is this important? Well, if we had something here, such as void print entity, which took in a const entity reference, which is usually the way you do this stuff. Yeah, and all it did is it logged entity.getX and entity.getY, and probably like maybe that, okay? And it did something like this, yeah? This get x and get y, if they weren't marked as const, you can see this results in an error because this is a const. So remember, when you declare const out the front, you're saying the value of that reference, so the actual entity can't be modified. And if this doesn't have const, it means I can do something like x++ here. And that'll totally work. Obviously, if I had const, that would be invalid, okay? But the idea is we need const there, or you should declare as const, because when you make methods such as this, you will get errors, okay? Very important. I know this video is probably going to be a lot to take in, so I expect you guys to probably follow along and just experiment. Honestly, experimenting is the best thing you can do. And you can try this out for yourself and watch this video multiple times. And obviously, when we actually start making the engine, I'll keep explaining things, not in as much detail as this, but we'll keep going with that stuff. Cool, we're at an hour. I'm gonna keep talking though, because yeah. So this is an example in which const should be marked here. Okay, cool. Let's talk about a few things. We need to talk about inheritance and a few other things. Let's quickly talk about structs though. So structs are declared like this. We might have a struct like vector, or I don't know, yeah, vector 2, vector 3f or something. So structs are very similar to classes. In fact, they're basically the same as classes. The only thing is they have no such thing as visibility. That's literally the only difference. So structs can have stuff like members, right? You can see they cannot have stuff like that. That's invalid for structs. We cannot have modifiers. Well, it's public by default. We can't have modifiers such as private or whatever. It's just public by default, okay? No such thing as structs with visibility modifiers. They can have methods. You can have methods. That's totally okay, yeah? It doesn't matter. You can have methods. So it's just that, yeah, you can have inheritance as well. They're kind of the same. But the general rule of thumb is you want to use vectors for stuff like this, where you just have a data type. It's just data. That's all it is, yeah? It's not a full system of things. You should only use it if you're just storing data. It's just as like literally a convenient way to store 3 floats in this case, and you didn't want to do it in an array for some reason, okay? Cool, so that's structs. I'm not gonna talk too much about them, but that is how they work. Cool. So, print entity, we didn't even see if that worked, so let's quickly print entity E. Well, of course it's going to work, but there's our entity. Fantastic. So anyway, that is that. Let's quickly cover arrays. So arrays in C++ are probably a bit different than in Java. There's a few ways we can actually express them, right? One of them is just simply by typing in int array and then typing in something like 50. That will allocate room for 50 integers. If we were to log array, rather size of array, we would get, what would we get? We would get 200, okay? That is the size of the array in bytes, okay? Which means that if our size is 50, yeah, of our array, and integers, the size of an integer is 4 bytes, 4 times 50 is 200, okay? So if we want the actual size of the array in elements, we usually go size of array divided by size of int, which is the data type of the array, right? And of course, that'll get you 50. Cool. This is very dodgy, because it'll only work in situations like this, and we'll talk about this in a minute. Another way to instantiate an array, rather, if I wanted to set its data, right, I can just do something like array 0 equals 2. That's a bit annoying. If I had all 50, let's just say we've got an array of 5, yeah? I want to set it up as, don't forget that semicolon, let's just say 2, 3, 4, 5, 6, right? So we've got 5 values. You can do that as well. And if we run something like that, it'll tell you we've got 5 elements. Fantastic. You can also not specify the amount of elements we've had, have it automatically decide what the size is, which is usually the way you do it if you're doing it this way. And then you'll get something like this. All right, cool. That's arrays. Now you can also do, this is basically done on the stack, right? Which means that when we get to the end of this, or that's where the memory is stored, when we get to the end of the scope, it gets destroyed automatically. We can also do arrays on the heap. Okay, so if we want to do that, we mark them as a pointer, and then we set it equal to new int, which is the data type, and the amount of elements we have. At the end of it, you should be deleting it. Now, you shouldn't delete it like this. You should actually use the square brackets to delete it, okay? That's just a thing that you do, okay? And then that will delete the data there. Okay, cool. So this is where it gets tricky. If I run this now, 1. Why on earth is our size 1? That sounds ridiculous. Let's check out the size of array. 4. Weird. Didn't we just set it to 5? What if I set it to 50? My goodness, it's still 4. I wonder why. Well, what is this? Don't look at this. Don't look at the fact that we're generating this. Look at this. What is this data type? It's a pointer to an integer. It's a memory address. A memory address on a 32-bit application is 32 bits. 4 bytes, which is why we're getting 4. If this was a 64-bit application, we would be getting 64 bits or 8 bytes. But the point is, we're looking at a pointer. So what I'm saying to you is there is no way to find out how big this actually is. No way, okay? Unless you've got something like unless you put like, there is a way. I'll show you guys a weird way, and this is actually how strings work, but if we were to count the amount of elements in an array, yeah, let's just say we had a result. I'm just going to show you guys one way you could do this. Int result for int I equals 0, or in fact I can just say nothing here. So while array at result, yeah, it doesn't equal -1, result plus. So if I just have this for loop here that does absolutely nothing except count everything, and I return this, and I set array at index, at the very last index, so if I allocate one more space of memory, okay, and then I set it at the very last index, I set it to something like -1, then what I can do is miraculously count the size of this array in elements. And if I run that, 50. Yeah? Pretty cool. And if I change this to something like 501, and then this to 500 or whatever, 500. Yeah? Pretty cool. Okay? It counts the size of our array in elements. So this is basically like a termination character thing. Obviously, it means we can't have -1 in our array, because if I was to put it at something like 100, then we get 100. Yeah? But the cool thing is, this is essentially how strings work. So a string is just an array of characters. So if we add a string, so you can set it's equal to something like hello, right? What happens is when you do this, it allocates 6 characters, yeah? Because it has the letters hello, right? And then it has a \0, which is a termination character. And then if you want to see how long a string is, it does something like this, okay? And that's how it knows that that data actually ends. Because if we look at this one more time, and we have something like an array of, let's just say, characters in this case, and this character string is equal to, again, something like hello. What happens is, and this conveniently takes up 1 byte each, which is nice to draw in memory. But if we have our RAM here, and we have, again, S is a pointer to the very first letter, so something like hello. And we have something like this. We've got a termination character at the end, a \, which I always forget how to draw that, but it's \, yeah. And then we might have other data there. What it does is, we know that it's, when we print it, for example, again, this is just a pointer to the first element. So how does it know when the string ends? Well, it looks for this. Well, it keeps going until it finds that. And when it does, it terminates. That's it. Okay? That is how it works. So then that's why you print out actually, you know, hello and not numerous other data. So what I'm saying is there is no way to see if an array is a particular size. Now, if we have an integer array, and this is an array that we've set to, I don't really care. It's just a pointer array, and it's set to new int, I don't know, 50 or something. Yeah. What happens is it allocates 50 integers for us. Again, it has no idea how much that actually is. It just allocates 50 integers for us, which is 200 bytes of memory. This A, yeah, this int A points to the very first address, which is right over here, and we might have something like 0 in there, and then we have like an address up here. Yeah, it points to this first array. When we call it like with something like A2, for example, yeah, and we use this square bracket notation, what it will do is it will go to the first, A will point to the first thing. Let me grab a different color here real quick. A will point to the first one, right? And then what it will do is it'll actually measure an offset of 2 integers. So of course, each integer is 4 bytes. So 2 times 4 is 8. So it'll offset our memory by 8 bytes. And then it'll read whatever is at this memory address plus 8. So FFA0 plus 8. Okay, otherwise known as FFA8. Yeah, that is what it will do. That is all the square bracket notation does. Which means you can use it with not just, you can use it with any pointer really. You don't have to use it with arrays. But that is how it works. So there is no such thing as an array index out of bounds exception in C++. If I do something like, if I have an array of 5 elements and I do something like array 6 lol, or even 5 would crash, look at that. We get the data at that particular array index. Okay, it doesn't care that we're out of bounds. There's no such thing as that, which is why you need to manually check stuff like that. There is something like std array that does actually manage stuff like that. I don't really like the syntax of it. I usually just use normal arrays. Everyone pretty much does. But yeah, arrays in themselves, just they don't know how long they are. So that's really important, which is why as I mentioned, we have the array, we have the count over here. This thing, right? As well as the command line arguments. Okay, cool. So there we go. That's hopefully a pretty good glimpse of arrays for you. Again, if you're passing in parameters, you'd usually be passing in this way. So if you want to print something and it's an array, usually you'd have a count as well. Okay, it's basically just that simple. All right. If it's just a string, so if it's like a const char string or whatever, you usually don't have to, because again, that string will usually contain a \0 unless you give it something like that. Consequently, one more thing I should probably mention is when we do something like that, remember the const is over here, not over here. So we can reassign this to a new string, but we can't access an index in it and reassign that to something like another character. Yeah, that doesn't work. Why? Because it's constant. Okay, so that's another thing that you should probably know. All right, cool. Anyway, quickly, just to wrap this up, I just want to cover a bit of inheritance and header files as well, and implementations, and probably namespaces. My goodness, this is going to, yeah. Anyway, so one thing I'll do is I'll actually make a new header file. Might as well kill 2 birds with 1 stone here. Entity.h. I'm just going to copy our entire entity thing over here. All right, cool. Now, let's talk about a few things. As I just mentioned, entities, or rather headers, are just, excuse me. Headers are just things that we essentially copy and paste, right? That's all they are. So that being said, if I want this data to be in here, I can just include it. I don't have to include it up the top either. People just usually do. I can include it right over here. So entity.h. Cool, and our program will run as expected. In fact, we're not even doing the right thing here, and I'm not deleting this array, lol, I am actually. But let's quickly print entity, and we'll make a new entity at like 5.5 or something, right? If I run this, cool, so it's working. Entity is clearly defined. What if I do that? What if I include it twice? Will that work? No, it won't. Use of undefined type, there's so many errors, okay? But the big error is the fact that entity class type redefinition, okay? What it's done, obviously, as you should know, is it's done that. It's copied and pasted it twice. And obviously this has the same name as this, so we get a problem, okay? How do we fix that? How do we stop people from including things twice? The first thought on your minds is probably, why on earth would anyone do this? This seems ridiculous. It does. But what if you have another header file which includes entity? When you include that header file, so if you have a header file called, I don't know, header.h, which happens to include entity, because it needs entity, because let's just say it does something special, like void print entity is defined here. This is a great example that I'm coming up with on the spot. But what if it does this, right? It needs the log as well, though. That's freaking annoying. Okay, let's print it doesn't. it needs entity because it should be able to do something like this, and it needs to know what the entity data type is, otherwise it's invalid. Kind of, but it's not really. But anyway, let's just pretend it is. If I do something like this, yeah, what do I end up with? I end up with a bunch of stuff. So let's do this. But I end up with a redefinition of entity. Why? I'm not including entity twice. No, I'm not. But I'm including header, which includes entity, and then entity itself is being included as well, because I want to do something like this here. How do I fix this? Well, you need to use something called a header guard. So a header guard is pretty simple. It basically says, if I basically want to define, let's just say class entity. Yeah, so I'm defining something as class. I don't have to define it to a value. I'm just defining its name. Class entity is a thing, right? What I want to say is, if not defined class entity. Yeah, so if there's no definition of class entity, let's define it. Let's, do all this stuff, and then let's end if. So what's going to happen is if it does this preprocessor check and it looks at class entity and it sees, oh, actually this is false, because it is defined, it's not going to do any of this. So it's only going to ever define it once, because when it defines it once, I mean, the first time when it tries to include it, it will look at this, it will see it's false. I mean, it's true because it's never been defined before. We will define it, which means next time it'll be false. So basically, if we had a boolean, it's done before. Like, if we had a boolean called first and we set it equal to 2, what the hell am I doing? Sorry. We set it equal to false, yeah? Or rather true, because this is the first time we're running something. And then we had if first do this stuff, we immediately set first equal to false. And this block will only run once, okay? That's exactly the same thing that is happening here. Exactly the same thing, all right? Great. So if I do this now and I compile this, it works. Yeah, pretty cool. Now this is a lot of extra stuff to do. So usually what you can do in most compilers is just write pragma once, okay? And that'll just mean it'll define it once. That's it. Pretty cool. And if I run this now, it'll work. Okay, fantastic. So basically every single header you declare should have a pragma once at the top. Every single header you declare should have a pragma once at the top. All right, fantastic. Or a header guard, okay? You don't really need both, but you can have either that or that standard header guard that I explained, which is the if and def. Cool. Now, why don't I want this like this? Why don't I want the header to be all this stuff? Remember, headers only get included. They do not get compiled. They never get compiled, which means that if I'm including things multiple times, this is being included in there, that's being included in there. This code is essentially being pasted everywhere, and it's a bit messy because it means it needs to get compiled in multiple places, essentially. So what I want to do is I want to make a C++ file. So the header file is like a prototype file. It just has definitions and stuff. Whereas the implementation, I'll call this entity.cpp, the implementation file, or the CPP file, actually has the actual code. So how do I do this? How do I implement these methods? Let's just pretend they weren't implemented. So they were like this, yeah? They weren't implemented, they just had definitions. So this just defines how to use the methods. I now know how to use these methods. I know when I call them, that takes in no parameters. It won't change the function, and it returns an integer, yeah? But I now know how to use these, but this has nothing to do with actually how they work, right? We put that into here. So if I just put this side by side, this actually probably is a terrible idea because of the face cam, so I won't do that. But entity age, yes, what we want to do is we want to include that file. All right. And what we want to do after that is, let's just call entity. Okay, so I should probably explain what I'm doing. What you need to do is, let's just say we're trying to implement the getX method here. Yeah, we can't simply go int getX because remember, as you probably know, that will actually make a new method because that's totally valid here. So what we need to do is we want to say, I want to access the getX method that is inside entity. Now remember, this is the same thing as if we had int count displayed here. Yeah. We know it takes in an array or something, but this is just a prototype, yeah? We have the same thing here. Now, the only difference, right, with this is that get X isn't in global, it's not in global scope. It's inside entity. Yeah, not in global, it's inside entity. So how do we tell it that this is inside entity? Well, we basically use a namespace. So we type in the name of the class followed by 2 colons. This basically is a namespace, I guess, operator or specifier, right? So this tells me that getX is inside the entity namespace. In this case, entity is an actual class. All right, cool. So this is now the implementation. I can return X. Usually this getters would be implemented in the header, but again, I'm just trying to show you guys how this works. Int get Y will do Y, and then the constructor is implemented similarly, right? We just don't have a return type, so it's just, and this might look a bit weird, but it's just entity, int X, int Y, and then we do this stuff. Now, why does this have an arrow? Yeah, why does it not have a dot? Is something that you guys are probably wondering. Well, that's because this is an actual pointer. Okay, basically, that is the data type of this, not that. That. So again, if you want to dereference it or something, you use that. Okay, otherwise it's the memory address. It's a memory address. That's all. That's really all there is to explaining it. That's why it's got an arrow, because it's a memory address. Yeah. If I was to log this, yeah. Now run this. Okay. That's unfortunate because of the logging stuff. Because this, yeah, I should explain why that doesn't work in a minute. But yeah, so it's just a memory address, right? But then there's our entity stuff. Now, what's different here is we've got a CPP file. What happens is this actually physically, it gets compiled. This code gets compiled. It includes entity.h and it gets compiled, okay? In fact, if I open up documents and I go to Visual Studio 2013 and I go to projects, Hello World, and then in Hello World, right, I look at, I need to quickly, what is this menu? Get out. I need to quickly just, before this drives me insane, because this is a new user, so I'll just check off hide extensions for known file types so we actually see the extensions. But in debug, you can see there's a main.obj and there's an entity.obj. That is actually, that gets compiled. Yeah, entity does get compiled into this obj file. We didn't have that before. We only had main before because that was the only CPP file that gets compiled. So header files do not get compiled. They just get included in places. They get pasted into CPP files. And the actual files that do get compiled are CPP files. The great thing is I only ever have to recompile this code if I change this code. Entity.cpp is compiled, good, it gets linked and referenced, and that's fine. If I only include stuff into stuff like this, yeah, if I include stuff into main, anytime this header file, anytime main changes, it has to recompile entity every time. Yeah? If I change entity or anything in this file, it has to recompile the whole file. Yeah? Whereas, by doing something like this, I'm saying this is like a modular component almost. Only compile this if I change something here, like change this to Y or something, yeah? Then you can recompile it. So it will reduce your compile times dramatically if you don't just have header only implementations and stuff like that. Cool. We're gonna wrap this up. I think I've covered everything I wanted to cover. Yep, I sure have. Static, we'll cover static stuff eventually. I don't think it's that useful. Like that, sorry, it is very useful. It's not that necessary now. I'll quickly cover it though. So if I had a public static, so again, I like declaring public static stuff up here. So if we had a static int a, yeah, the way we actually declare it is in the CPP file, we need to use the namespace, or rather the type of the data first, then the namespace, then a, and then we can set it to something like 2. All right, that's how you declare something as static. And then if you want to use that, so if I want to print or log that, I go entity. So in Java, you go entity.a. Here, just go entity : or namespace a. And then if I run this, we'll get 2, okay, at the bottom, which is our static thing. So that's probably one thing to know because you've got this stuff. All right, let's quickly talk about namespaces. You can surround things in namespaces, okay, and you should. A lot of things you'll see in tutorials for Hello World or C++ is people will type in something like using namespace std. Don't do that. Don't do that in a global scope. okay, it's not really a good idea. Okay, I actually personally don't mind having STD everywhere. By the way, for those of you who don't know, if I do something like this, basically it means that I'm in the STD namespace, I'm using it, so I can get rid of this and just use cout like that. Personally, I don't mind having STD there. I kind of think it looks good actually, because I know which cout it's referring to. But more importantly, if I do something like this and I make my own function called cout, that's going to create all kinds of mayhem, okay, if I'm using namespace STD, because suddenly cout will have no idea whether it's referring to my function. As you can see, it'll tell me it's ambiguous because it's referring to two things, okay? So don't do that, okay? Put stuff, if I make this, I can put it in a namespace called Cherno. In that case, it will completely negate that, and that'll work now. Unless I happen to be using namespace Cherno, because that's what that video taught me how to do, lol. That beginner C++ series I took. Yeah, now suddenly it's ambiguous again, all right? Don't do this. The only time it's pretty much acceptable to go using, and especially don't do it in header files. Seriously, I've seen some pretty like long, it's pretty serious problems that take ages to fix because people put this in header files and then that gets included everywhere, and anyway, don't use this stuff in global scopes. Essentially, the only place where it's pretty much acceptable to use stuff like that is actually inside a function. So if I had a we'll put back std in this case, it really should be here. If I had a function like let's just say I did have a log function, or I had a function called print, right? And this print function for some reason needed to use std cout. Let's just say it prints a blank line in this case, and I didn't want the stds here, or I use this is a very long function that uses a lot of this and I don't want to have to specify std. You can just put using namespace std right here, and that's totally all right, okay? And you can do something like this, and this can be like print line or something, right? That's acceptable. Do not put them up there, please. It's not a good idea. Okay, cool. That's going to wrap this up. I'm actually going to make a follow-up video tomorrow about how to use Visual Studio, because I didn't expect this to go for an hour and a half, but it did. I hope you guys have a pretty good understanding of C++ right now. I realized I didn't do any inheritance. Let's quickly cover inheritance. So the way that inheritance works is if I make, it's kind of the same way that it does in Java, but yeah, there are some notable differences. So I'm making player.cpp and player.h right now. So player.h, again, I'm pragma oncing because that is how we roll. Let's include our entity. So if I make a player class and I want it to extend entity, or in Java, you know, type in extends or whatever, you put a colon and then you put public and then you put entity. All right, just like that. So if I want to have, I'll have a public constructor or something. If it's a default constructor, you'll automatically call the constructor here if it's a default constructor. It's not though. So what you'll probably have to do is actually call, and you don't have to do this here. You can actually implement it. So if we implement player here, so let me just zoom in. If I implement player over here, yeah, what I should be doing is calling the base constructor. I can do that simply by using this colon, right? And then calling base, oh no, rather not base, but entity with the correct parameters, so I can make sure that the player spawns at 5, right? And then obviously the player will spawn at that particular location, right? Or the positions will be set like this. Okay, so that's how it works. You just use this colon and then that's basically super for you. Now, if I have something like, let's just say I want to call, okay, this is another useful example probably. I have my own version of getx for some reason. So this is what it looks like in the implementation. This is what it looks like, and then I return something like x. Okay, so first of all, we get an error. It's incompatible with whatever. We get some stuff done. Well, actually, that's only because of this. But the point is, this is not actually overriding the other one. If we wanted to override it, we need to do a few things. We actually don't change anything here. But if we want the if we want getx to be overridable, we need to mark it as virtual. Okay, virtual, like that. That means that it is that means that we can override that. So if I mark those two as virtual, now this is overriding the other one, right? And if I do something like, I don't know, I return this, but I also want to call entities getX. So in Java, that would look like this. Sorry, entity super.getX. To do this here, you actually just type in entity getX like that. It looks a bit weird, but that's how it works. Okay, and that will call the, so I could just do that. This is gonna look a bit weird, but you could just do that, yeah? And then in that case, it will actually just, we might as well not have overridden it, obviously, but that will return that getX. Okay, cool. And I have to cover destructors quickly as well, but if I make a player now, so I'll have to include player. If I include player and I call player P like that, and then I print entity, which of course will print the player, 5, right? And if I go into player or something and I change this to 5080, it should print that 5080. All right, cool, fantastic. So it works the same way. As you can see, print entity takes in a where is that even? That's in like header, isn't it? Oops. Yeah, it takes an entity, but I've given it a player and it still works because the player is an entity. Cool, fantastic. There we go. So one more thing I want to cover is destructors. Now I talked about how we can delete things. So if we make a new player on the heap like so, yeah, we can delete the player. So what actually happens, well, what actually happens when we delete something like the player? Let's just quickly push that in. What actually happens when we delete the player is it runs the player's destructor. So what I mean by that is we've got a constructor which runs when the object gets created, and we've also got something called destructor. It's declared like this. So it's basically got a wiggly line, which is the tilde key. So it's just above tab next to the number 1, just to the left of the number 1 on your keyboard, right? And this is like the constructor, but it's called a destructor because it runs when the object gets destroyed. So if I implement one of these, and I do something like I log in, well, we'll just see out because I don't think I've got the log function, destroyed player. Yeah, and I do something like this. I probably don't even have that anyway. All right, and I run through that. You can see that our player gets destroyed, right? So let's log something like not destroyed, or I'll just log 1. I don't even have to have the quotes. And 2, and you'll see that what actually happens is we get destroyed in between 1 and 2. Yeah? What's interesting is that this, and you can do stuff in the destructor, so you can delete other objects. So if the player had another entity and we declared it on the heap and we wanted to delete it, we can do that there. But the point is, that's the destructor, right? If you make a destructor over here in entity, and you decide you want entity to have a destructor, it is incredibly important that you mark it as virtual. Because if you don't mark it as virtual, it's not going to run, okay? If you don't mark it as virtual and you call player as destructor, the entity's destructor is not going to run. If you mark a destructor as virtual, yeah, and you have another destructor in player, like so, yeah, when you call this destructor, yeah, it will also call the destructor of entity. So it'll destroy everything, which is important because as you can see, some of these things that we have that might need being destroyed might actually be declared here, and they will never get destroyed unless this runs, because this destructor will be in charge of destroying that. Okay, so that's very, very important. Virtual destructors. Okay. Anyway, that being said, that's pretty much how it works. Now, if we declare this object on the heap, right, and we don't delete it, it's still gonna get deleted, right? It's just that it gets deleted at the very end of our scope. Okay, so a better example will probably be to run this. Let's just say we had void a, and I run this. So if I run this over here and I print entity, yeah, and then I run that function, okay, and I run this. Destroyed player, right? And where does that happen? That happens in between 1 when the thing ends and just before 2. So it happens at the end of that scope. So you can see the destructor still runs, obviously. It's just that it gets done automatically. All right, cool. Now there are a few things we haven't covered, such as the difference between like these include things, or as you can see, we've got quotes here and angular brackets here, and there's a few more things we haven't covered, but that should be that should set you up for C++ basically for the series. We'll be doing a lot more advanced things, obviously, but hopefully this will teach you the basics of C++. So please experiment with it, right? I'll make another video. So the next video will be teaching you guys how to use Visual Studio, because I didn't really do that this episode and didn't expect it to take so long. But give me some feedback. If you have any other questions that you want me to answer in the next video, please just leave a comment in the description, and I'll be sure to address that. And yeah, see you guys in the next episode. Goodbye.